Okay, Ohm's law. And we've got some students, for the young people, if you ever think you've broken Ohm's law, you haven't. Voltage equals current times the resistance. If I have 10 volts on 1 ohm, it's 10 amps. And we'll go back to that. If I look at the curve of where this is voltage and this is current, the slope of this is the resistance. If you get a meter and you put it on there, it takes it at one point and it takes the voltage, divides the voltage by the current, and that gives you the resistance. You can run it where you have a continuous voltage and then get a linear representation. So a resistor is linear. A diode, on the other hand, okay, so this is a diode. VF is the forward voltage. If you look at a diode, it's real simple the way it works. If this is connected to a battery, this is positive and this is negative, the current flows in this direction. This is the anode and this is the cathode. The way to remember this is this looks kind of like a negative. This points the direction of the current flow. So if we apply a voltage that increases like this, you're going to have low current, and then when it hits a certain point, it's going to turn on. For a silicon diode, this is 6 to 7/10 of a volt. So if you look below that, it's turned off. If you look above it, it's turned on. You can take a model that does something like this, and it's not far. 6 or 7/10 of a volt, it turns on. Here is a way to look at this. Say I've got a dam, and I've got a river flowing. The river can't get to the bottom until it goes over the dam. That's the bias. So I have to bias. I have to put this much water in order to get any flow. All this water that I've used to bias the dam doesn't serve me any purpose. And I'll show you how important that is later when we start talking about efficiency. Once the water goes over the dam, it flows at the same rate that it's coming in. So it turns on. If we look at a simple three-phase rectifier, you've got three stator coils and these diodes. So when I put a positive voltage from the anode to the cathode, I turn the device on. So if you here are the three phases. These are three sinusoids. Let's take as an example this one. At this point, the voltage is positive. So this diode is positive with respect to here. So as soon as this gets 1 volt above B plus voltage, let's say that this is 14.7 volts. So when this gets to, I told you earlier that it begins to turn on at 6 or 7/10. It's turned hard on at a volt. Our diodes are at 100 amps. The forward voltage is about a volt. So let's use the volt. So when this voltage here becomes 15.7, this diode turns on, and this is the current flow. It comes through this diode, back here, and closes the loop. Okay, when this voltage falls below this, when I lose that 1 volt bias, this diode turns off. So I don't get any backwash. Because if when I'm trying to push current in, I have a hole in the dam, then I don't have the efficiency that I want. Okay, so this is phase 1. Let's go to phase 2 now, which is here. When this comes positive, current flows through the load and the battery, coming back through here. So what you've got is each one of these is pumping. And each time it does, it throws a little more voltage and dumps current into the battery. And as I said, you've got pictures that show that. There's another thing, another feature of this diode. The diode I showed you looks like this, and then at some voltage greater than 600 volts, it breaks down. This junction is very thin. It's a PN junction. It's a thin 10,000th of an inch piece of silicon. So when the back voltage gets so much, it will break that joint. It'll break that junction over. So when it hits, say, 600 volts, and this is, you're old enough to remember this, where you didn't have Zeners. 50DN doesn't have Zeners. So those go out to a certain voltage, then they break down. That's a bad thing because it'll destroy the device. There's another diode that we have in our light and most of our heavy-duty machine. It's called an avalanche diode. The avalanche diode looks very similar schematically. You still have the cathode and the anode. The current flows in this direction, but when the back voltage, when the reverse voltage gets to a much lower level, let's put a back here, it turns on. This, for our diodes, is 24 to 29 volts at 100 milliamps. So here we've got 100 milliamps, and this is 24 to 29. So at that point, the diode flows current in the reverse direction, and here's why. The current in an inductor cannot change instantaneously. The current in an inductor, as an analog, the voltage on a capacitor, stays fixed. As soon as I take the current off of an inductor, the instant later, the same amount of current is flowing through that because it stores energy in the form of a magnetic field. With a capacitor, as soon as I've got a voltage on that capacitor of 10 volts, as soon as I remove that 10 volts, it stays at 10 and starts to decay. So let's say that I'm running this alternator at full field, putting out 100 amps. As soon as I remove that load, in an instant, I still have all of the magnetic field stored in the stator as well as the rotor in the field. So it's going to take a while for that energy to drain out. So as soon as you remove that load, the energy is fixed. So the voltage is going to shoot up. The voltage will shoot up. In the old days, you're at, say, 14.7 volts. The voltage will go up, then this will decay with an exponential time constant. That time constant is like 300 milliseconds. This is 125 volts. That's a lot of energy. So in 1985, Remy introduced the first centralized load dump protected alternator. In the old days, you had an alternator that would generate this load dump. So every place you had electronics on the vehicle had to have their own load dump protection. So all of the electronics had to have something that would clip that voltage down to a manageable level, because the cost of an electronic device is a function of the breakdown voltage. The higher the breakdown voltage, the higher the cost. So by putting load dump protection everywhere, everybody had to pay that money, 25, 50 cents. Okay, in 1985, with the 9SI CS130, Remy introduced an alternator with centralized load dump protection, where instead of using standard diodes, they use these. Okay, so let's go back here to this. As soon as I open this, the voltage is going to run up. But as soon as the voltage runs up, it's going to hit this Zener, and it's going to clamp it. So it's going to go out to 24 to 29 volts. In actual practice, it's 30, 31 volts. So now we have, back 30 years ago, Remy sold the first centralized load dump protection alternator. We create the load dump inside. So we stopped that, and now the whole vehicle could put the money back on the table because we're protecting to 40 volts, so each of the individual electronic components doesn't have to. So that covers the Zener, the standard diode. All right, let's move into regulation. This is a regulator. It's a thermostat. This is set at, I can't read it, 72 degrees. That is the set point. If you look at the critical parameters on a voltage regulator, obviously we have to have the right set point, and that right set point is so that we can properly charge the battery. The battery only charges optimally in a very narrow band. If the voltage is too low, it takes too long. If the voltage is too high, you damage the battery. So one of the functions of the regulator is to regulate the voltage. Another is, if there is a fault, to indicate that fault. We want to tell the driver that you have a problem so that you can get service. The other critical parameter is load regulation. You know in your house when the air conditioner turns on how the lights will kind of dim down? That's load regulation. What you'd like to have in an ideal situation is, this is current, which is the load, and this is the voltage. If this was a perfect regulator, no matter how much current load I put on there, the voltage would stay the same until it ran out of energy, and then the voltage will drop. This is really not the way the regulator works. In fact, the regulator generally has a bit of a drop. So set point is easy. You put a voltmeter on the output of the alternator and you read what it says, 14.7, that's the set point voltage. Okay, load regulation is where you take, and there are different conventions. Let's use 90% and 10%. You take the set point at 90% load and at 10% load, and load regulation is the difference between, it's this delta right here, the difference between the loaded voltage and the unloaded voltage at a specific range, 5 to 95, 10 to 90, different conventions. That is spelled out in the specification. Okay, now let's talk about how the regulator works. In 1968, the first solid-state voltage regulator came out, and it was designed by dinosaurs. Some of them are no longer with us. Those guys were my mentors. They were the real frontiersmen. These guys made electronics. That was back in the days where they used scalpels and rubylith in order to image these silicon wafers. So they'd get a light and shine it through this red ruby transparency, and that would mark off the wafers, and then they'd etch them. So they could make semiconductors overnight. So in 1968, these guys started the first solid-state voltage regulator. The customer was Delco Remy. Let's go back to our drawing and talk about the diode trio. Now this was 68, so this was before we had Zener diodes, avalanche diodes. So take the same. This went to plus and the loads and the battery. this, oh, I got it drawn already over here. Yeah. Sorry about that. Here's the rectifier I told you about. This is the diode trio. Diode trios are on the old SIs, the 36, 22. This is obviously old technology. The current for the field, this is magnetically coupled to the stator. When the alternator begins to rotate, and I'm going to assume that all of you have been through the Alternator 101. So when the alternator begins to rotate, the stator cuts the flux of the rotor as it goes through, and it converts that into current. The current pushes into a load to get the voltage. Okay, so again, you've got three phases that are pushed from the diode trio into the field. When this is a switch, and I'll go into some transistor work in a minute. Just assume this is a switch that goes to ground. So when this switch is closed, current flows through the field. When that happens, it induces a field into the stators, which makes the juice. Okay. If I go, this is a comparator, and a comparator is a nice device. It's real simple. It's got one output, two inputs. When the voltage on this is higher than the voltage on this is low. When the voltage on this is higher than this, it's high. It's real simple. In this case, it's an inverter. So let's put this to the sense, which goes over to the battery. Let's put a battery here. And it connects to the battery. This goes over to the battery. This is where your charge current goes. So when this voltage gets above the set point, the thermostat temperature, this voltage becomes higher than this one, which opens this switch. When this switch opens, the current decays through this, and then as soon as that happens, it's going to drop this voltage. So the output is pop, 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 pop. And if you look at it, it's switching on the ripple here. So here's the set point voltage. When I'm above, it turns the output off, on, off, on, off. So it's a real simple regulator. Now, let's go back over here. Here's the trio. This goes to the field, and this goes to that transistor. Here's the battery. It goes through an ignition, through an indicator lamp, then to a switch. Okay. Now I'm going to get into fault detection on a monofunction. People call this, the regulator I'm talking about is by a number of names. One is white package. You got white package, black package. White package is because in 1968 it was made from a material that was white in color called alkyd. Remember, this was one of the first, well, it was the first solid state piece of electronics that had the temperature range. So it had to be special. So it's white package. The other is trio version. Another is monofunction. Monofunction because all it does is regulate. Okay, so I turn the key on. As soon as the key is turned on, remember I'm below set point. Oh, one other detail that I didn't tell you, but it's important here. The charge voltage of a battery is 14.8 volts. I need to push 14.8. But if I take the voltage off, the open circuit voltage of the battery is 12.8. So I have to overcome 2 volts in order to get any current into the battery. So let's take that example. This is 12.8 volts. I go in to start the vehicle. The first thing I do is I turn it to the on position. In the on position, this is now, let's say our set point is 14.7 volts. So this is now 12.8. This is greater than this, so it's pushing current into here, and it turns this switch on. When that happens, it pulls current through here. And this is a 3-candle power bulb, which is about 35 ohms. Now we go into the crank condition, and the engine starts and the speed starts coming up. As soon as the speed starts coming up and it forward biases all these diodes, now current begins to flow through the trio. When that happens, this voltage comes up. Before that happens, this is let's say a 2 ohm field. So I've got 35 ohms and I've got 2 ohms, so I've got about 37 ohms. So the light is going to turn on. I got about a volt here and virtually nothing here. So the light turns on with full brilliance. That is no rotation. But as soon as the alternator begins rotating and turns on by all these forward biasing, now this voltage goes all the way up to the charge voltage, which is 14.7. And remember, I've got this long lead back over here. So this is 14.7. This is 14.7. So the light goes off. So the lamp isn't smart. That's why it's a monofunction. You're doing the charge voltage, but by virtue of where you have the lamp, that's what turns it on. Now I'll draw the distinction in a minute between that, the white package, monofunction trio version, with a trio-less version. The question that I had when I first got into regulators is, why do you have to switch this? Let's do some Ohm's law work here. We got a field that's magnetically coupled to this. These are the stators. Let's say that this is a 2 ohm load, and this is a 14.7 volts. Let's say we have 100 amps output. 100 amps output at 14.7. Let's say my switch down here has 0.7 because it makes the math easy. So I got 14 volts across 2 ohms. That gives 7 amps, right? Going back to Ohm's law. Well, this is 100 amps, so that means that the transfer function of this alternator, for every amp of current that I put at the input, I've got 15 amps. 7 times 15 is 100. Okay. So if I now put, instead of 14 volts, if I put 7 volts here, that means I'll get 50 amps here, right? It's a linear relationship. So the best way to do that is to get a power supply and make this, put some kind of a switch here, and make this 3 amps, 3.5 amps. And that will give me 50 amps output. Okay. At this switch now, let's say this is 14 volts. Now I've got 7 volts here, and I've got 7 volts on my switch. So now I have 7 volts times 3.5 amps. Remember, okay, Ohm's law of power is equal to IV. So now I've got 24.5 watts that I'm dissipating in a voltage regulator. That's a lot of power. On the other hand, if I make a switch, with this switch I either turn it on or turn it off. So when I turn it off, since there's no current, there is no power. When I turn it on, this voltage is low. If it's 0.1 volts and I've got 3 amps, that's 0.3 watts. So the reason why you switch regulators, any power supply that you've got uses a switching regulator. High performance audio equipment that has a high output power generally uses switching because it's more efficient. You don't burn up that energy, burn up that power. So that's why our regulators switch. The easy way to do is just to change the voltage. But when you do that, you have a really bad power dissipation, like greater than 10x. Well, we're dissipating the power on a backplate that's like that. You can't dissipate 24 watts with that small area. So the reason why we have switching is when it's open, there's no power because there's no current. When it's closed, there's low power because you have a high current but low voltage. So as long as this is small or this is small, your power's low. That's why you have the switching. All right. So you heard about the white package, which is the monofunction. Let's talk about the multifunction. The multifunction goes by a lot of different names: black package, PWM, MOSFET. In 1982, REME was the power in heavy duty and light duty alternators. Then REME started getting competition from the players that we're fighting with today. GM said, we're going to give you 3-year moratorium. And that is, we will continue to buy your product and only your product for 3 years. But at the end of that 3 years, you guys got to get your act together. Because they went from 68 to 82 without getting any new stuff. So those guys came to Delco Electronics and said, hey, we need some magic. Help us to make this new machine. And the new machine was the 9SI or the CS130. It's a 130 millimeter machine, 93 inlet. It was going to be the 29S back then. Small, efficient, cheap, all of the right things. So we started working on a multifunction. I was a green engineer, and Tom Merrill said the diode tree, it also had to be high quality. Tom Merrill said we need to lower the warranty. So we started looking at the warranty, and the first thing that stood out is that diode trio had a 3% warranty. 3% of the alternators that we sent out came back because this failed. Well, I, being ignorant, said, well, why don't we just get rid of that? And everybody laughed and said, well, you can't get rid of that. Between 68 and 82, there were a lot of advances. This was one, the Darlington, and I'll tell you a little bit about that, but also the electronics technology improved remarkably. 68 to 82, that's when you had the integrated circuits becoming commodities. The 555s, all of these things became commodity parts. So we set about to make a new alternator. In 82, the X body, which was the Citation, just came in. It was introduced, Jeff will remember because he is that old. The lines, yeah. Remember the gas lines in the early 80s? The gas went up, so GM responded to make this smaller displacement engine instead of longitudinal mount, transverse mount, and they had all these things, and it was a great idea, but it didn't work. The X body was the Citation. Was it Citation? Is my story. Yeah, Citation. In the showroom, as soon as the people would go and start the engine, it would shake, just like that the vehicle, the boat I told you about. That was idle shake. And the engineers at GM, when they were trying to figure it out, they started pulling connectors. That's how their troubleshooting was. And when they pulled the alternator connector off, the problem went away, and they said, hey guys, obviously it's an alternator problem. So we had to fix the idle shake. We were also, back in the day, we were using 4 ohm fields. Well, with CS130, we needed to go to a 1.8 ohm field. And you can't use this technology, and I'll explain that in a minute. So we got together with REME, and they said, here's what we want. We want high efficiency, low cost, high performance, all these things, and we just started designing that and developed the first multifunction regulator, and that's in your pictures. Basically, the multifunction was different. In that it had what's called a MOSFET, and again, I'll go through the MOSFET in a minute. And it was also a high side drive. Remember what I told you earlier, when you disconnect the battery, the first disconnection is the ground? Look at for safety reasons, look at the alternator now. The whole alternator is at ground potential, with the exception of a very small area, and that's the field. So if we tie the field, going back here, let's say we connect this directly. I want to get rid of the trio because that's 3% warranty. So let's tie that directly to B+. But now, when this is open, the field is connected hardwired to B+. So all around the field is surrounded by ground because the alternator is at ground potential. So now there is a possibility of having corrosion because I have a positive voltage here, negative everywhere. So with moisture, remember the slip ring interface is copper, carbon, potential, medium. Now I have corrosion. I have galvanic cells. It's a mess. So what you have to have is a switch that will, when you're not rotating, when the car is in the garage, there's no potential, positive potential here. Okay, so that's what the advantage of the trio is. When it's not rotating, there's no field current. When it is rotating, you don't have to worry about that. Okay, that's why we have a MOSFET. MOSFETs in 1968, I don't even know if they'd been invented. But now a MOSFET, now I've got the switch. So put the battery back here. This is now a switch. This is at ground potential. So when the switch is open, ground is ground, so there's no corrosion. So it's perfect. The high side drive allows you to get rid of the trio, which is cost, fasteners, reliability, a lot of reasons. So the first thing we did is got rid of the 3% warranty, got rid of the footprint there. Remember I told you how the regulator turned on and turned off? According to this, here's your set point. That's not the smartest way to do it, because this, with load, this will increase. So your load regulation deteriorates on a bang-bang regulator. If, on the other hand, you can go through a filter and then send this through a comparator, now you can get a direct reading. This, you're using the ripple, this is a ripple switch to turn it on and off. It's bang, 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 bang. On this, I can now take a long filter and apply that here, and it's really refined. I mentioned to you earlier about load regulation. This one at 70 amps had a load regulation of 400 millivolts. So it dropped 400 millivolts. The 9SI CS130 at 100 amps was 150 millivolts because it used a different scheme. But in order to do that, you have to make pulse width modulation. Pulse width modulation this is on, this is a full period. In this case, this is 1 millisecond. This is 2 milliseconds. So this is a 50% duty cycle, which goes back to what I said earlier. At a 50% duty cycle, your half of the voltage is impressed across the field. Let's go back here a minute. Now I put the switch in the high side. Here's the field. Now I'm going to explain why you have a diode trio. So I push current, this is a switch. When I close the switch, current begins to flow in here during this time. So I'm filling up that field with magnetic energy. Now, at a 50% in this case, it turns off. So now the current has stopped. Remember what I said, that current in an inductor stays the same at t equals 0, t plus. So this was 3 amps. So it's going to continue, and it's going to flow. And it will go through this exponential decay. Well, the time that it does this is very short. So really what you've got, it looks like a direct current because it's just got a small amount of ripple in it between when this time. This time on the 9SI was 2.5 milliseconds. Well, 2.5 milliseconds isn't enough time for the energy to dump out. So it looks like we're applying a direct voltage there, but we're not. We're switching, but we're switching so fast that the field diode and the inductance of the field makes it look like DC. So now instead of having the 25 watts, we now take that down to 2 watts, and nobody knows the difference because we've got this. Okay. The original black or white package regulator had 6 transistors, 3 or 4 resistors, and a few capacitors. In 1982, the voltage regulator had a MOSFET, a field diode, a digital integrated circuit, and an analog integrated circuit. It had a digital processor, not a microprocessor. So now we can do some magic. If you've just got half a dozen transistors, monofunction, there's not a whole lot that you can do with it. But when you get into the fact that now I've got comparators, shift registers, counters, timers, lions, tigers, and bears, I can do all kinds of magic. So then Remy said, let's get rid of our NTFs. Because back then, 90% of the failures were trouble not found. In order to do that, you have to have a more comprehensive fault diagnostic. With the 9SI, Remy went out to the field and said, if the light doesn't come on, don't take the alternator off. But in order to do that, you've got to flesh out your fault better. Remember, the only fault that we had with the indicator lamp, the monofunction, was no rotation. Okay, no rotation is the fan belt's broken. Remember? I've got 12 volts here going through the switch, going through the bulb. I turn it on, and I can't get rotation to bias up the trio to turn everything off. But what about overvoltage? Overvoltage, as I generate overvoltage, the battery comes up, so there's no voltage delta across the lamp. So I got nothing. Well, what about undervoltage? Undervoltage. I can't do any of that with the trio. But now that we have an analog circuit and a multifunction with a PWM, we can go out there and look by putting a comparator there and monitoring the voltage. So when there's an overvoltage looks like this. here's over voltage. Here's the back of the regulator. If this device fails, it fails short. So now the output of the alternator, is a function of the load current and the speed, because you've got the performance curve that does this. This is really bad, because there's nothing you can do inside the regulator except tell that you have a fault. This is over voltage. Over voltage means I've shorted the output. I have no control. There's nothing that I can do. I can't disconnect anything. But we want to know about that because all of the electronics is now going to have an elevated voltage. The battery is going to boil, and it's a bad thing. So we tell the driver, you have an over voltage condition. Remember, on the white package, both of those voltages would come up at the same time, and you couldn't, since there was no delta between them, the light wouldn't come on. Okay. Let's take one called failsafe. To iterate again, the whole REMI idea was, I'm going to give you better fault indication, and if the fault light doesn't come on, don't change it. That's how they attack their NTFs. So we've got over voltage. The other one is, now I have an alternator. Let's talk about two things at once here. This is an alternator with a regulator in it. This is B+, and this is the load. Real simple. If the battery and the alternator are electrically close, you can sense the voltage right off of the back of the alternator. But on heavy-duty applications, the battery and the alternator are remote. They could be a half a volt off. They could be 10 meters off. We've seen that. Let's talk about a little resistance here. All wires have resistance, so there's a small amount of resistance, and the longer the wire, the more resistance. Let's say, for talking purposes, that this was 14.7. That's the set point. If I'm dropping 0.5 volts across here, I'm only getting 14.2 volts here. And what I said earlier, that's not optimum, and that gives you it takes longer to charge. So if you've got a vehicle that's doing a lot of stops and starts, a delivery vehicle, you'll have what's called discharge at idle. Your vehicle at the end of the day will discharge because I've lost a half a volt here. Okay. So the way to solve that is to run another wire to run that sense into the comparator. Remember I showed you they had the comparator, and then this went into a PWM, and that went into the MOSFET. So now this is going to connect to here. So this is set for 14.7, so this will be 14.7 plus 0.5. So this will go up to 15.2, and it will compensate for that loss. This is, a Kelvin connection is a 4-wire connection, where you force and sense, force and sense. This is kind of a half Kelvin because the ground generally has less resistance because it's the vehicle body. So you don't have much drop across that. So that's the reason why you have on heavy duty, because the battery is seldom in the engine compartment. On light duty, the alternator and the battery are this far apart with a wire that's that big around. We saw 20 meters between the alternator to the battery and back on this Daimler that we looked at in April. So it's real. So with external sense, it compensates for this. Now, what Delco Remy wanted was something that would switch automatically, because now we can deproliferate. Part numbers cost money. So the first 9SI, or CS130, had internal or external sense. If the external sense is connected, it's used. If it's not connected, it automatically reverts back to internal sense. Okay. What happens if this opens? This can open by losing the B+ power connection on the back of the alternator. Remember I told you earlier? This is 12.8, which is the open circuit voltage. So if I'm not charging it, this voltage here will drop to 12.8. When it drops to 12.8, the regulator says, I'm below set point, so charge. So the voltage here begins to increase. Well, since there's no way for this to get pulled up, this voltage will continue without bound. The sense line is connected. So the sense line is seeing 12.8, and it's 12.8, which is below V set point, so it says charge. Because I've opened the loop. That's a bad thing. Now, it's not a bad thing for the vehicle because the vehicle load is not connected. So it's not going to blow your ECU and your clock and the radio and all that stuff. But remember, we've got in here Zener diodes. The voltage here will increase to 50, 60, 80 volts, and it will pop every one of these diodes. So that's no good. So there is a condition called fail-safe. Fail-safe does two things. It has another set point in here, another comparator, which is like 19 volts, that goes back over here to the switching circuitry, and it says if this voltage, whether I have sense or not, goes up to 19 volts, shut it off. So now it's switching at 19 volts. But the other thing you want to do is to fail-safe is regulate and indicate. So with fail-safe, you regulate and indicate. Okay. Now we have a 1985, 86. We have an alternator that can put out 100 amps, which is phenomenal back then. We also wanted to have, we've got an overvoltage and a fail-safe, but we also want to have something that indicates if we have an undervoltage condition. Let's say one of our diodes is bad on the rectifier. So it goes to full field, but because I'm losing a third of the current, then my voltage is going to drop. So the answer to that is have an undervoltage. So undervoltage is about, remember, this is 12.8 open circuit. 11 volts, 11 and a quarter plus or minus a quarter is where the battery has lost its life. So you want to indicate that. But you don't want to indicate it all the time. And here's why. If the load, a transient load, is put on at low speed, your alternator is going to go to full field and the voltage is going to droop a little bit. So with the undervoltage, it was conditioned with two parameters. One is low voltage, that 11 volts, but the other is high speed. So if you're below 11 and a quarter volts and above, going back to the performance curve, up here, you got more current available than the loads would absorb. So up at say 3,000, you got plenty of current. So if something is loading the engine or loading the alternator, or the alternator is damaged, now I want to know about it. So I'm below a voltage and above a speed. That's why you have on under voltage 2 parameters. Let's go back to load response control. The way an alternator works is it takes mechanical energy and converts that to electrical energy. Every time you go through an energy transfer process, you're going to lose part of that energy. The guys in 1982 on the citation, when they pulled that product connector off, that pulled the wire out, they essentially disabled the alternator. So the electrical load that was being serviced was not being serviced now out of mechanical energy. Let's say that you've got a 100 amp alternator at 15 volts. The amount of energy is significant. 100 amps, and that's a small alternator by today's standards. At 15 volts, that's 1,500 watts of electrical power. For talking purposes and to make the math easy, let's say that it's 50% efficient. So now that's 3,000 watts of mechanical power. This is electrical. There are 746 watts per horsepower. So that means that in order to service this load, that's 4 horsepower, which is a pretty good size. That's a large lawnmower engine. So the alternator exerts that amount of energy, torque, to the drivetrain. So what was happening on the citation, I told you we had 2 things. Let's. Whoa. You guys stand up while I draw the picture. Give yourself a break. Okay. Yeah, next time I do this, I'll draw a better picture. But I did get a good picture in the handout. Back in the day, all of the drivetrains were longitudinal. In 1982, first transverse mount, citation, load response, or the problem with the idle shake in the dealership. All vehicles have a characteristic resonance. The resonance is determined to a large extent on the distance between where the torque is being applied and the wheels. So this has a small L. This is a transverse mount. Here's the engine. So this L is from the front wheels to the back wheels. This is half the distance between the front wheels. So what you've got here is long L. Here's short L. So with a short L, you have a higher frequency, and you can do the math. But long, lower frequency, higher frequency. So if you look at the drawing, here's what was happening. Here's frequency, and here's the magnitude. Here's the characteristic resonance of the vehicle. Here's the idle speed. So as soon as they put a load on, it instantaneously sucks the energy out of the drivetrain, and because it's at idle and there's an underpowered engine, it begins to walk back. The speed begins to decrease, and it starts to walk up this. And during that time, it's a noticeable shake. This could be manifest with the power door locks. The rear defog was a bad one. The seats, the movement of the seat. So all of that caused this objectionable engine shake. Here's what they did. They solved it. You guys know 5-phase, problem description, containment, root cause, corrective action, verification. The first thing they had to do was fix the problem because the citations were not selling. So they did something, and this was back when fuel was expensive relative for the time, and they were taking all the weight off the vehicles. They essentially, if you look at this, they essentially lowered the Q. Now we had a vehicle, and I'm telling you, what I'm going to tell you is true. Here's the steering wheel. The first thing they did is they put a 10-pound bumper damper. Do you believe this?
I believe it.
They put a 10-pound bumper damper, and all it did was lower the resonant frequency. It detuned the body. Back then, 10 pounds was a lot of money. Now you had this long steering column, and as the driver would feel it like that. So they put, this is before the airbags, obviously, they put a 2.5 kilogram steering wheel damper. So that was brute force. But it allowed them to sell the vehicles. It killed this problem. But it's such an unelegant solution. That's the birth of load response control. So now that we had this regulator that was intelligent, we could monitor some things. And all we did on the load response control is a real simple energy conversion. Instead of drawing energy in the form of kinetic energy from the engine, we drew it in potential energy from the battery. We've just spent all of our time putting energy into that battery. Let's just use it for that short time that we need it. If you look at your handouts, that's what LRC does, is during this first time, because all you want is enough time for every step back you take in speed, the idle speed control loop will get you back there. So it's not like you got to do something radical. Just slowly go to the load. And you're taking energy here and you're putting energy here. And the problem went away. Now, once you take the genie out of the bottle, there's no putting it back. Today, the next application for load response control was the Cadillac. Cadillac wasn't transverse mount, it wasn't small engine, but they had a very complicated idle speed control loop. So if you look at the speed of their loop, this was their ISC loop. This was LRC. So as long as your damping element is slower than your idle speed control, you keep it in a critically damped or an over-damped condition. You take it from an under-damped to an over-damped or critical damped. So this damping of load response control now is being seen to have many uses. We had one with Hyundai last year where they had an idle stability problem, not related to any of the things I've told you. We dropped the LRC on it and it went away. So this slowly going into regulation and a period of a second or two or three or four, it's not a big deal because the battery doesn't recognize that short time because the battery is looking for a steady state voltage. Go back to your transistor. I told you a good model for a diode. This is an NPN transistor. NPN, collector base emitter. The way this works, a real easy model, is you have charge carriers that go from the base to the emitter. And as they go, they take 100 of their buddies from the collector. That beta in this case is 100. So if I put 1 milliamp in the base, I get 100 milliamps in the collector. So if you look at your diagram there, and if Herman was here, I'd have him run through the equations. Scott, why don't you run through the equations? If you look at that diagram, what did I say? This is equal to 0.3 volts with a beta is equal to 25. And then I've got an RB, right? In the diagram there?
Yes.
Okay. So the amount of base current it takes, this is 7 amps. So that means I have to put 0.28 amps here. So if I've got 14 times 0.28, I've got 7 watts here and 2 watts here. So it's almost 10 watts. No voltage regulator that I know of has ever used a single transistor because the bias power. This is 7 or 8 watts and 2 watts. Remember I told you got to keep it below like 5 watts? So the answer is, let's put 2 of them together. Now this is IB, this is beta, and this is beta. So now I get IC equals beta squared times IB. Great, love that, but remember I told you that this is 0.7 and this is 0.7, this is 0.1, it's really 0.2. So now the voltage here is about 1 volt. So at 7 amps, I've got 7 watts. Still too high. Now back in the old days when you were using a 3-4 ohm rotor, that was okay because your power went down. But with the CS130, with a 2 ohm load, we needed a lot more current. Then came the MOSFET. MOSFET is metal oxide semiconductor field effect transistor. I told you about the diode. You build the bias, the dam, the water's got to go over it. On the transistor, every charge carrier that goes into the base carries 10 with it, piggybacks 10. That's how you get the amplification. A MOSFET works entirely different. Say I've got a hose and I've got a valve on that hose and it pinches it. When I apply voltage to the gate, I open that channel. When I take the voltage away, I close it, so I'm blocking it. The other thing that's good about a MOSFET, this is what a transistor looks like. A MOSFET looks like that. So a MOSFET is resistive in nature. So I don't have this biasing problem that I have with another part. We have a MOSFET rectifier bridge where we're replacing diodes that have that 1 volt with MOSFETs, and the MOSFETs have half of that. So we've cut the losses on our MOSFET rectifier bridge in half by using a different device. So a MOSFET, you apply voltage to the gate, and the equations are there, and it opens the channel. The good thing about it is you can get MOSFETs that go down to 5 milliohm. They have MOSFETs today that are less than 1 milliohm. So for every 1,000 amps of current that goes through it, you only get 1 volt drop. Today, with 35 amps, we've got 1 voltage drop. So 1 volt drop. So a MOSFET, that's the reason why we're changing our diodes with the MOSFET rectifier bridge. Today, nobody uses transistors because of the problem that I told you, power. If we get to, let's say we get to a, let's make the math real easy, 100 milliohm device. So it looks like 100 milliohm is 1/10 of an ohm. So if I have 7 amps, going back to that same 7 amp, 7 watt, so 7 amps power is equal to I squared R, so this is 49, this is 4.9 watts. And 100 milliamps is high. Today we've got 10 milliohms, which would take it down to 1/2 of a watt. The point is, with a MOSFET, if I have a device that big that's 50 milliohms, a device that's twice that big is 25 milliohms. A diode, I can have a diode this big or this big, and it's still 1 volt. The height of that dam is the same. You can't fight that. With a MOSFET, you don't have that. That's the reason why MOSFETs are in all regulators. Here's a problem you got with a MOSFET. The current is equal to transconductance times VGS. Okay. The current through the drain is equal to the voltage across here times some constant, some gain factor. It takes about 10 volts to turn this device completely on. Okay, so now let's say this is 12.8. Ideally, this would be 0 volts. If it's a perfect switch, this is 0 volts. So that means this voltage is also 12.8 volts. 12.8 going through a wire is 12.8. But remember, I need 10 volts to turn this on. So what I've got to do is I have to come up here to drive that gate. Now I have 10 more volts to drop across here. That's why all of the regulators have voltage doublers or charge pumps, because you have to take the voltage above the highest voltage that you've got. If you don't do that, you have high power dissipation because of the fact that this potential is at this potential and I need 10 volts to turn it on. That's why on the MOSFET rectifier bridge, you have to have a charge pump. On all the voltage regulators with a high side device, you have to have charge pumps. All of that stuff costs more silicon. Today we have several versions of regulators. The old kind, the white package, we're still buying almost 500,000 of those a year. Real simple, half a dozen transistors, you know that. Half a dozen transistors, it's a real cheap regulator, but it does the purpose. The other is 2 of our suppliers have ASICs, application-specific integrated circuits. That's where they've taken all of the resistors and transistors and op amps and all that, and they've integrated that into their own custom silicon. They paid somebody hundreds of thousands of dollars to build a piece of silicon for them. That's an ASIC. We also have ASSPs, which is application-specific standard products. Application-specific standard products are like the ST Micro MW8, which is like a TO220, double-wide TO220. We've got those in all the regions. We have 6 suppliers today. All of those 6 suppliers package these ASSPs, this double-wide MW8. We now have, and we're in production with 2 parts that are LIN, Local Interconnect Network. The way LIN works is, let me back up. In the old days with the monofunction, there was no communication. When we went to the 9SI CS130 with pulse width modulation, we had another level of control where the ECU could control us and we could send information to the ECU that would tell kind of what we were doing. Remember back the drawing that I showed you, that in order to turn a white package on, you have to go through a 3-candle power bulb. Well, that makes it hard because it's difficult. You can get that kind of current from an ECU, but it's not convenient. But with the 9SI, the high side drive black regulator, we could now bring that input into a comparator, which is high impedance, and it's no problem. So now the ECU could control what we were doing, or the key could control. The other thing is we could send our state of PWM to them. That gave them a little bit better idea of our faults, in addition to the overvoltage, undervoltage, fail-safe, fail-soft that I already talked about. Then in '97, we came out with the RVC, now the COM. With that, this is PWM. On the COM, and this is Setpoint. So here it went from, let's say, 13.5 to 15, and so at half of that, you take half the voltage. So now the ECU can give us a very refined set point. The other thing they can do, let's say they send us a 10% duty cycle on the COM terminal. 13 volts is close to where the battery voltage is. I've been charging at 14.8. So as soon as that happens, as soon as I drop that voltage, the alternator shuts off, because now I drop below the set point, so it says, hey, shut off. When you go into passing gear on a vehicle, you want all of that energy to go there. So as soon as you hit the wide open throttle switch, the ECU recognizes that and sends a low COM. Okay? Now let's look at energy management. Today, the brakes on a car work by friction. So you get wear, but also heat, and it doesn't make sense. So let's use the alternator as a dynamic brake. Remember I told you that it's 4 horsepower at 100 amps. Okay? Now I take my foot off of the accelerator to go to the brake, shoot it to 15.5, because it'll never get to 15.5. The alternator will go to full field. It will take all that energy that you're telling it to pull from the engine, and it'll suck it from the engine, and it'll be a dynamic brake. So there you say, and that's one of the things we're doing today with Hyundai. They're using that C terminal for energy management to get fuel economy. So it goes back to what I said earlier about load response control. Once you take the genie out of the bottle, the guys in the car divisions are going to do whatever they can with that. So they're using this COM for any number of things. There is another one behind that, and that is computer control using bit streams. Today, this is all PWM, ones and zeros, but it's duty cycle modulated. Here's full field, here's less. If we can now go ones and zeros, where I have a word, and that word might be 8 bits, so 111001, that now contains a set point information. I want 14.75. I can also take another bit, another byte, 8-bit byte, and put in that load response control. Give me another one, Dankert. What's another parameter that's on LIN? Current limit. So I can take all those, and those are 8-bit words. With 8 bits, you can get 256 possible combinations. So now the computer says what I want. I want a load response control of 2.5 seconds, a set point of 14.8, and current limit of 6 amps. So it takes these and it converts that thought into 110011, and it converts all those. Then it takes that, all these words, and stacks them. So now instead of having all these, like, remember the old printer cables? had lots of pins on them. Well, they don't have that now. Now they're serial communication. So take those 8-bit words and stack them behind each other, and then shoot those down one wire. So on the LIN, the ECU says, "Yo, regulator, are you there?" "Hey, I'm here, I'm here." He said, "I'm going to send you some information. Prepare for it. I'm ready. You throw it, I'll catch it." So now he sends all that information, and the regulator takes it, grabs each one of those bytes, and stores it. Then, behind the curtain, takes that and says, "Okay, now this is 110111. That means set point 14.8. Okay, so it now says set point 14.8. It takes that other byte, it decodes that and says load response control 2.5. And it's an interactive communication. Patrick brought up a good point yesterday. Why would we do that? One, a good reason is now I don't have to have all those wires. I can convey 6 or 7 or 8 pieces of information with one wire. The instructions on this LIN travel at 19,200 bits per second. CAN is another advancement to LIN, is 250,000 bits per second. So now, instead of having a stupid, dumb, let's call it dumb, that's less offensive, a dumb regulator, now we have a regulator that's an integral part of the engine management system, because now I have such a big device on there. Okay, let's talk thermal shutdown. We take cooling air from the airstream about 125 or 130 degrees C. Junction temperature in our regulators can only go up to 175. At 175, the plastic pieces start expanding super fast. It's called the glass transition temperature. You don't ever want to operate above 175. But with the heat that's coming in, we don't have much margin between 130 and 175. So one of the features that, if you want to call it a feature, that we've developed is a thermal shutdown. It's on most of the regulators today, the ASICs and the ASSPs, and that is to have a temperature when you get to that point, the regulator stops regulating or drops the voltage to where it allows it to cool off. As soon as you stop generating current, then the alternator cools off quickly. But one thing you want to make sure you don't do is indicate a fault. So with thermal shutdown, the alternator throttles back to cool it down, but doesn't give a fault indication. And I already said my closing 5 minutes ago, but let me say it again. From 1968 to now, regulators have changed. Instead of being a simple device, now they are an integral part of the energy management system. Charge on decel, wide open throttle shutdown, communication. Now we are on the critical vehicle buses in LIN, and ultimately we'll be in with CAN. That's a good thing for us because it gives us value. We don't want to compete in a white package world because then you're chasing labor. What we want to compete in is an area to where we can add value based on our years of experience and our ingenuity.